So this video is going to be going over the definition of the derivative, and specifically we are talking about the first derivative. So basically, in order to talk about the definition of the derivative, we're going to start with a topic that you've been discussing for a few years at this point, and that's going to be the secant line. So we have a point here, we have point A, and then we see a line where the slope of that line is going to be the slope at point A. So that is going to be the tangent line. So I'm going to label A, and then we can label that as the tangent line. Now, in order to relate this definition back to something you're more familiar with, we're going to need a second point. And we'll call this point, why not, B. Okay. The reason why we're creating a second point is because we are going to use a secant line to talk about the first derivative. So we have a line that is passing through 2 points on this curve, okay? And we'll label this as the secant line. Now you've had a formula for this in order to find the slope of this secant line. It's also known as the average rate of change, and that is going to be y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. Now, in order to relate this to the definition of the derivative, let's go ahead and label point A. We can call this x down here, and then we will call this f of x. So that means the coordinate point for A will be x, f of x. Because this curve, it can be function f, okay? Now at B, if we go from, we have a distance between A and B, we're going to call this change in distance delta x. Okay, literally the change in x. So if I want to label the horizontal coordinate for B, that is going to be the distance from the y-axis. That is going to be x plus delta x, okay? So the coordinate for B, the x coordinate will be x plus delta x. Now that means the coordinate for this point, the input is x plus delta x, and if this curve is a function of f, that means the output will be f of x plus delta x. Now on the vertical side, the change from A to B is going to be f of x plus delta x. Okay, so we're using delta x in order to show the change from A to B. Okay, now on the side here it says a secant line slope could be calculated to approximate the tangent line slope, given the average rate of change that you've been working with for a few years for now. Now let's go ahead and use what we have from this graph and plug it into our secant line slope. But let's go ahead and label some things. So point B, we'll call that point 2. So this will be x sub 1, and then this will be, I'm sorry, that's an output, so that'll be y sub 2. And then for point A, we'll have x sub 1 and then y sub 1. So now if we directly substitute what we have from this graph, y sub 2 is going to be f of x plus delta x minus y sub 1, which is the output for point A, which is f of x. And then in the denominator, x sub 2, sorry, I labeled B incorrectly. That should not be x sub 1, that should be x sub 2. So x sub 2 is going to be x plus delta x minus x sub 1, which is just x. Okay. All right, so we have our average rate of change between A and B. So the next part is asking, how can we improve the tangent line slope at point A? Because if we look at the slope of the secant line, it is significantly steeper than the slope of the tangent line at A. And the goal is to create a way to find the slope of this tangent line. So if we look at B, let's say that we slide B to here. If we created a new secant line, then the slope of that secant line is closer to what the slope of that tangent line is. So let's slide it again. So I slide it a little bit closer, and I'm still using delta x as the change in delta x. But each time I slide b, if you notice, delta x is becoming smaller and smaller and smaller. So how close can we slide this to a in order to make the slope of that secant line equivalent to the slope of the tangent line? Well, let's make delta x approach 0. So we are going to continue to slide that point B as close to A as we can until delta x, or not until delta x is 0, but it's approaching 0. It's getting really, 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 really close. Now, this is what creates the definition of our derivative, okay? So we have the limit as delta x approaches 0, and if we apply that to our secant line slope, this will give us the exact value of the slope of the tangent line at that point, okay? So the numerator is f of x plus delta x minus f of x. And then if you notice in the denominator, we have x plus delta x minus x. That just means we have a delta x left in the denominator. And this is what's used to find the derivative for a function, aka the slope of the tangent line at a point, okay? All right, and you do have to have this memorized. That's why we go through this process, is hopefully the fact that we went through this process, it's using a formula that you've had for years at this point. We're just substituting new variables in order to satisfy what we need to solve for in calculus, okay? So given f of x is equal to x squared, find the derivative function of f of x using first principles. So this is called first principles. It's also called the limit process, and it's called the definition of the derivative. So all three of those mean the same thing. Depending on the scenario, a question could present it any one of those three ways, okay? So let's go ahead and start. So we have f prime of x is equal to, and remember, the best way to recall is to write it down as much as possible. So f of x plus delta x minus f of x divided by delta x. All right, so let's go ahead and substitute. So we'll have the limit as delta x approaches x. Now, if we look at this, this says f of x plus delta x. F of x plus x plus delta x, that is your input. Okay, we are inputting x plus delta x into f, okay? Which means we are going to substitute x plus delta x into any input variable that is within this function, okay? So since I have x squared, my input is x plus delta x, I'm going to have x plus delta x squared. In class, I used another example. I did 3x plus 1. Now, if we were to begin the limit process for 3x plus 1, my input will still be x plus delta x every single time, which means when I apply the limit process to 3x plus 1, that becomes 3x plus delta x plus 1. So x plus delta x just replaces any of the x's within your function. Or the variables can change. Whatever the variable is, it's going to be replaced with these two values. And then minus f of x. F of x is a direct substitution. F of x is equal to x squared. And then we divide by delta x. So whenever you're evaluating a limit, try direct substitution first. If we directly substitute 0 for the limit process, we will always have a 0 in the denominator, but for limits, always try substitution. But for this case, it will not work. So we need to expand, combine like terms, and the goal is to remove the delta x from the denominator so that we can evaluate this limit, okay? So from here, we will double distribute. We have x squared plus 2x delta x plus delta x squared, and then minus the x squared divided by delta x. I got on people in class for this. You need to be able to expand these quickly. So a plus b squared is equal to a squared plus 2ab plus b squared, okay? So the limit process, when you're dealing with quadratics, this is always going to show up, and that's for this part. All right, from here, oh my gosh, huge mistake, huge mistake. I forgot my limit. Always include the limit until we use direct substitution. All right, so I'll go ahead and include it down here. All right, so we have the x squareds cancel out, and we are left with 2x delta x plus delta x squared divided by delta x. Whoops. All right, so every single term has a delta x, so we can cancel out a delta x. Feel free to factor if you want to. The same thing will occur. So we have the limit as delta x approaches 0 for 2x plus delta x. So we had delta x squared, so we divided by 1 delta x, therefore 1 is left. Okay. All right, now we can do direct substitution. We have 2x plus 0, which is equal to 2x. Therefore, 2x is the first derivative of x squared. Okay, so this is how the limit process works. Now, part B says find the derivative of f of x at x equals -4. So if we think about this, if we were to draw a sketch of this parabola, and we want to know what the derivative of f of x is at x equals -4, this is asking what is the slope of the tangent line at x equals -4. Well, we have a function for that. We literally have a function where we can plug in any x value and find the slope of the tangent line for that x value, okay? So we're looking for f prime of 4, which is equal to, I'll plug in 4 into my first derivative, which is 2 times -4, which equals -8. So the slope of the tangent line at x equals 4 is -8. The next part, find the slope of the tangent line to f of x at 3. Same thing. All we need to do is find f prime of 3, plug it into 2x, and we get 6. So the slope of the tangent line at x equals 3 is 6. So because we have f prime of x, we can find the slope at any point. All right, that needs to be super, super clear. Part D says write the equation of the tangent line. All right, so we're back to this tangent line. We need 3 items: your slope, your x-coordinate, and your y-coordinate. All right, we already know the x-coordinate. It's going to be 3. And we already know the slope. We found it in part C. That's going to be 6. The only piece that we are missing is the output. So to get that, we need to go back to the original function, and we need to plug in 3. So f of 3 is equal to 3 squared, which is equal to 9. So the tangent line is going to be y minus 9 is equal to 6 times x minus 3. All right, hope that was helpful. Next video will be on the alternate form.